Okay, it's Brian, and this is our Friday lecture. It's Duck and Cover, Tales of the Atomic Age. And since it's Friday, I do Freddy Fridays. I got a little Queen music for you. And this is We Will Rock You. Students, you are stuck in your houses, hoping maybe we'll come back to class someday. You got a mask on your face when you leave your place. It's a weird dystopian world these days, saying we will, distance, dun, dun, we will, distance. Oh yes, it's because this lecture, bizarrely, was about the dystopian future that I imagined when I was your age, and I thought for sure it was going to be nuclear weapons that were the doom of us all. And when I ask people your age kind of what you're worried about, you're not worried about nuclear weapons, which is a good thing. You're worried about environmental degradation, which is kind of a bad thing. But also, people have been worried about pandemics, and we're getting a taste of what illnesses that span our connected globe can look like. Crazy. So I'm sorry that you are living in this time, but I'm hopeful that some lessons come out of this that help us figure out how not to give in to this sort of situation, just as in my age, people were able to figure out how to keep the worst of the things that could have happened from coming about. So Duck and Cover, Tales of the Atomic Age. And I first became aware of nuclear weapons when I was 8 years old. And I'm going to talk about that later as part of the story. But before I get there, I want to do a quick bit of homework review. So let's look at a couple things from the homework assignment that you folks handed in. And one question that you did was this one here about the New Horizons spacecraft. And it had 10 kilograms of plutonium-238, and the total activity was this. And the question was, what was the thermal power from the plutonium source? And I talked about previously how you can have a chunk of toasty plutonium that's just warm because of the fact that it's decaying and it's giving off kind of like thermal radiation, etc. It's giving off heat that you can use to power your spacecraft. It had an activity of 6.3 times 10 to the 15th becquerels. Well, remember, 1 becquerel is 1 count per second, 1 decay per second. Okay, so you had 1 decay per second. Each decay gave off an alpha particle with this energy. Ultimately, all of that energy turns into thermal energy. So computing thermal power as just the number of decays per second times the energy per decay, boom, and there you go. Now, another problem I wanted to think about was this one here having to do with the gamma scan. So if a gamma scan gave 3 millisieverts to a patient's lungs, how much energy was deposited in the 1.2 kilogram mass of the lungs? And remember that let's see, this is a beta decay. So for beta particles, 1 gray is just equal to 1 sievert. So if it's a dose of 3 millisieverts, that's also 3.0 milligrays. And remember, 1 gray is 1 joule per kilogram. So there's not an equation to use for this per se. You just have to know what the units mean. Now remember, gray, joule per kilogram of absorbed energy. If you have a situation where you have other kinds of radiation that have a different, like RBE, relative biological effectiveness, the dose in sieverts could be different than the dose in grays. I want to do a quick calculation. Previously, I mentioned this idea that you have a certain amount of internal radiation that comes from like food you eat. And actually, it turns out a pretty significant fraction of the internal radiation that you receive comes from potassium-40 in your body. Okay, so potassium-40 in your body decays, and it decays by emitting a beta particle. And when it does that, it gives you a dose. It gives you a dose. And I want to know, how big a deal is the potassium-40 dose that you give yourself? Now, a couple of stages in the calculation. First off, we're going to do this. Okay, most of your internal radiation, we say, is due to a single isotope, potassium-40. It's got a half-life of 1.28 times 10 to the 9th years. The body contains this much potassium by mass, and of that, this much is potassium-40. We're going to do a series of calculations. First off, we're going to calculate what is the total activity in becquerels of a 70 kilogram human. Then, we're going to figure out how much energy that deposits, because each decay makes a beta particle that's that big. And if we assume that you absorb 40% of it, what dose and what dose equivalent will you receive in 1 year? And the reason for the 40% figure, it's complicated. But anyway, that's a reasonable value for this. And I just want to mention this was something that I had people do for a past exam problem. Now, when you solve this problem, you're not just going to look for an equation. What I want you to do is just reason about it. These are all things you can do with proportionalities and ratios and things like that. Just reason it through. Don't worry too much about the equations. But I want you to think about this problem. I want you to pause for a minute. I want you to start it. I'll be back. Let's break this long problem up into a series of steps. Okay, so what I want you to do is go through these in turn. Figure out what is the mass of potassium in the body, and then what's the mass of potassium-40. Given that, how many atoms of potassium-40 are there? How many decay each second? What is the activity in becquerels? What is the energy released in joules? How much energy is absorbed each second? How much in 1 year? And then the dose equivalent in 1 year. So we've broken this problem up into a series of bite-sized pieces. So I want you to take a minute, start working through those steps. I'll be back. Well, of course, to get the mass of potassium in the body, we're told that your body contains 0.35% potassium by mass, and we're assuming a 70 kilogram human, so that's easy to calculate. If we calculate the total mass of potassium, then we compute the percent that's potassium-40, so we can compute the mass of potassium-40. And then if I want to know how many atoms of potassium-40 are in the body, what I'll do is this. I know the mass of potassium-40, and each atom has a mass of 40 atomic mass units. So I know the total mass. I can figure out the mass of one atom, and so I can figure out how many atoms there are. How many decay each second? Remember that the decay rate, the activity, which is the number of decays per second, was like 0.693 divided by the half-life times the number of atoms. So if you have the number of atoms, you can work out the decay rate, and the decay rate, or the activity, is the number of atoms that decay every second. That is literally the activity in becquerel, so these are actually the same calculation. Then how much energy does each decay release in joules? Each decay releases 1.3 mega electron volts. How much energy is absorbed? And we can convert that to joules, of course, so we'll put that in joules. That's how much energy decay releases. How much energy is absorbed by the body? That's the energy per decay. Then you're going to multiply that times the number of decays, and you're set. That's the number, the amount of energy that's absorbed by the body each second. And then for 1 year, I'm just going to multiply by the number of seconds in a year. And that's going to get me the energy that's absorbed. Then what I'm going to do is remember the dose in grays was equal to the joules of energy absorbed divided by the kilograms of tissue, and it's a 70 kilogram person. So you're going to compute the grays, and given that it's a beta particle, grays is just equal to sieverts, so given the dose in grays, I can compute the dose equivalent in sieverts. A lot of steps. None of them is that hard, but I want you to step back through and make sure you understand where each step comes from, what each step is calculating, where each step leads. And here's a couple of relationships that are useful for you. That's my basic equation for activity. The atomic mass of potassium-40, 40 atomic mass units. 1 atomic mass unit is this much. And if you have to convert from mega electron volts to joules, 1 mega electron volts is 1.6 times 10 to the negative 13th joules. So take all that in hand, complete your calculation. And here's the numbers that I get. 0.245 kilograms of potassium in the body. Then it's this much of potassium-40, dividing it by the mass of individual atoms, or the mass of an individual atom. I get this number of atoms, which is okay, it's pretty small. That's significantly less than a mole. So how many decay each second? I calculate the activity of 7,600 atoms per second, 7,600 becquerels. Each decay releases this many joules. So in 1 second, I take the number of decays per second times the energy per decay, and I get this is the number deposited in the body per second. Multiplying by the number of seconds in 1 year, it's this much. Dividing by the mass, I get 0.28 milligrays or 0.28 millisieverts. This is approximately 10% of your yearly dose from all sources. So if you're trying to separate yourself from sources of radiation, you're going to have trouble because 10% of your yearly dose you give to yourself from potassium-40 that is in every cell in your body. So radiation is literally part of your life. Now, that's radiation that's naturally occurring, but I want to talk about radiation that is not naturally occurring. And over the course of my life, I was probably exposed to more radiation that wasn't naturally occurring from nuclear weapons tests that happened in Nevada and other western states. Actually, we had some in Colorado, which is sort of an interesting bit of history. But in the 1950s, there were a lot of above-ground nuclear testing in the western United States. 1950s and 60s. And that produced a whole bunch of not naturally occurring radiation. And when you get this not naturally occurring radiation in the environment, you can get very large doses. Check it out. The maximum dose that workers taking part in the cleanup in Japan for the Fukushima reactor, 250 millisieverts. That's 80 years of a typical dose. And actually, that's how they got the number. One of those workers increased their lifetime dose by a factor of 2. And once you got there, they're like, okay, I think you're done. Crazy. And that was not naturally occurring radiation. In that case, drinking milk was actually not such a great idea. This much activity, or this much of a dose from drinking a pint of milk. Crazy. Now, if you live in the United States, when they're doing tests in the western United States, and then the fallout from those tests, the radioactive isotopes that were produced, went across the United States, look at the typical doses that people were getting. The highest doses in the United States were 160 millisieverts. That's comparable to the doses that people got when they were participating in the Fukushima cleanup. So it was a fair amount of exposure to fallout. And a lot of this was happening during the years when I was young. So I was certainly exposed to a good deal of that. And if you look at isotopes in the atmosphere, one of the things that we talked about with radiocarbon dating was the idea that the amount of carbon-14 in the atmosphere is essentially constant. And it is, except for during that spike right here, which is when all the above-ground nuclear testing was happening. You can see big spike in the 1960s, big spike in the 1960s. And then there was a test ban. This is the Partial Test Ban Treaty. And that kind of like stopped having above-ground nuclear testing or limited above-ground nuclear testing. And then there was a steady fallout or steady fall off in the amount of atmospheric carbon-14. But in future years, when people are computing radiocarbon dates, if they're things that are in this era, there's going to be a lot of extra carbon-14 in the samples that people measure. That's one of the ways we've left our mark upon the world. So coming back to this duck and cover tales of the atomic age, well, I first found out about nuclear weapons when I was 8 years old, and I used to sit up in the attic and read the encyclopedias because who doesn't spend that kind of stuff when you're 8 years old? And then we had these encyclopedias, and inside the frontispiece was a series of woodcuts. And so it's like, oh, here's the progress of humankind. So here's fire. Here's the printing press. And then there was this one here, and I asked my mom about it. I said, Mom, what is that? Is that... It's like broccoli, or what is this? And she said, oh, that's the bomb. And I said, what is the bomb? And she proceeded to tell me the whole story. And I was just so disheartened and scared about this and realizing there's all these crazy weapons out there. And I was certain, like until I was, after I was in college, that we were going to like destroy ourselves this way. Now I want to talk about the story of atomic weapons and atomic power. And remember, we looked at this graph last time of stability. We said if nuclei are too big, the Coulomb repulsion is too strong, they want to break apart. They want to break apart. We saw that. Well, it turns out certain atoms that you can make spontaneously break into smaller pieces, and you can do that in a chain reaction. And it works like this. If you take uranium-235 and you let a neutron sidle up to it, so a neutron kind of like sidles up to it, insinuates itself into the nucleus. Now it's a nucleus of uranium-236 that's highly unstable. It immediately breaks into two smaller nuclei. But given that heavier isotopes have relatively more neutrons per proton, two things happen. One is these nuclei are incredibly neutron rich. The other thing that happens is you have extra neutrons. So one neutron comes in, hits uranium-235, makes two radioactive offspring, but it also makes 3 neutrons, and each one of those neutrons can condense a uranium atom to fission. And each one of those fissions produces 3 more neutrons. And each one of those neutrons can produce 3 more fissions, which make 3 more neutrons. And so you can have a rapid increase. Like you have one atom fission in, and then all of a sudden they're all going. You get this exponential growth in the number of atoms which are fissioning. You can think about this. Relate this to the coronavirus. Like if each person infected 3 other people, you would have an incredibly rapid increase in the number of infections. And that's what's happening here. Each atom can convince 3 other atoms to fission. And so you get this very rapid exponential increase of the number of atoms fissioning. And so a dramatic release of energy in a very short time. Now, it turns out uranium does this, but you can also do this with heavier elements than uranium, and you make those in nuclear reactors. Inside a nuclear reactor, there are all these neutrons floating around. If one of them hits uranium-238, it absorbs it and makes uranium-239 that subsequently beta decays to make neptunium-239. But neptunium-239 will subsequently decay into plutonium-239. And so inside a nuclear reactor where all the neutrons are floating around and you've got uranium-238, you're going to produce plutonium, which is a fissionable material. It's a new element that doesn't exist in nature. It only exists where humans have created it, and we create it in nuclear reactors, and you can use plutonium to make nuclear bombs. So if someone says they want a reactor, maybe they just want the energy, but maybe they're looking to take plutonium, and you can make plutonium to make bombs out of. So whenever there's a nuclear reactor, it is making bomb fuel. Now, you can be careful and you can keep track of your waste, but you need to be very careful, not just because it's toxic, because of its radioactivity, but because it can be used to make weapons of mass destruction. So we have to pay that some mind. Now, when you have heavier elements, they have relatively more neutrons, and we talked about that. So when you take this heavy nuclei and you split it into lighter pieces, you end up splitting into pieces that are neutron rich. And if they're neutron rich, they're very radioactive. And so when you split uranium into smaller atoms or smaller nuclei, they end up being highly radioactive. And check this out. One of the common daughter products that you get is barium-141. Well, barium-141 has a half-life of 18 minutes, which means its activity is through the roof. It's crazy radioactive. And the stuff that it decays into has a half-life of 4 hours, and then a half-life of 32 days, and then finally you end up with something which is stable. So when you have a nuclear reaction, you end up producing these very short half-life daughter products that are incredibly radioactive. And so nuclear waste, or the fallout from a nuclear explosion, is ridiculously radioactive. And that was the big problem with the Fukushima reactor. You started out with something which was mildly radioactive, and you turned it into something which is insanely radioactive. And there's some of the isotopes that are given off in making nuclear power or nuclear weapons that are particularly worrying. Iodine-131 taken up by the thyroid, very short half-life. Cesium-137 taken up by all the cells in your body because it's similar to potassium, half-life of 30 years. Strontium-90, similar to calcium, taken up by your bones. And so these isotopes are taken up by the body, incorporated into your body, and can give you difficulties with radiation dose years down the line. So when you have a nuclear reaction, you end up producing this dangerous waste, and it's dangerous for a long, long time. Now, right before World War II, it became really, really clear to scientists that you could do this. If you had a chunk of uranium-235 in one place at one time, it would spontaneously fission with the release of a great deal of energy. And the scientists who discovered that were German. Well, that was like before World War II. Things were heating up in Europe, and the Germans were being difficult. So the German scientists made this discovery. The German state was actively warring against its neighbors, and all the major sources of uranium in the world were controlled by Germany at that point. So Einstein was persuaded by his colleagues to write a letter to the President of the United States and say, we know if you get enough uranium-235 in one place at one time, it'll go boom. And the scientists who figured it out are German, and Germany has basically access to all the major supplies of uranium. And so we need to think about this. We need to think about this seriously. And so it led to this amazing project in the United States to develop an atomic weapon that subsequently was used against the Japanese. And then versions of them were subsequently tested in the South Pacific. And this is a typical explosion. This is in the South Pacific, so I can see palm trees and I can see ships. This was a test of a weapon out at Bikini Atoll. By the way, Bikini Atoll, that's where the name of the bathing suit comes from. Because one was like they've split the atom here in this nuclear explosion, and now people have split the bathing suit. But also I think the idea was that the force of the bikini on people's on the male psyche was comparable to, you know, a 15 kiloton explosion. Crazy time. Anyway, that you would name swimwear after this. This is nuts to me. Anyway, this explosion, 15,000 tons of conventional explosives equivalent. Not 15 tons, 15,000 tons. Crazy. And then you end up producing a flash of light. You end up producing a tremendous blast wave. And inside this cloud, ridiculous quantities of radioactive isotopes. And so you have this like deadly cloud, and that stuff goes up in the atmosphere and comes down in the surrounding area and rendered these islands basically uninhabitable. Now, you can actually get more energy out of a fusion reaction. Like if you took a deuterium and you hit it onto another deuterium, you can produce helium-3 plus 1 neutron. The problem, and you get a lot of energy out of that. The problem is these things are both positively charged. They repel each other. How can you force them together? You would have to have them going very fast indeed, slamming into each other at very high speeds. How do you get things moving really fast? You do it with a nuclear explosion. So if you take a nuclear explosion, a conventional fission weapon, and then you wrap it in a bunch of material that can do fusion, you get extra energy. And then for good measure, you wrap that in kind of another layer of uranium, which absorbs neutrons and gives you even more explosive yield. And those are so-called hydrogen bombs or thermonuclear weapons. And those are much bigger. Here's a picture of a test. And this isn't 15,000 tons. This is 15 megatons. 15 million tons of conventional explosives is what this is. And at this point, the fireball, which is as hot as the surface of the sun, has a width of about 4 kilometers. So the fireball is like bigger than Fort Collins. And so anything inside that radius is completely vaporized. This is kind of crazy. And these are the kinds of weapons that we were developing in the 1950s and 60s. And when I started becoming aware of them, they're crazy. I mean, the destructive power of that is just absolutely insane. But meanwhile, what I was hearing was that so if there was a nuclear war on our soil, all we need to do is duck and cover. And I got a chance to participate in drills like this where you get to get underneath your desk. We had a bomb shelter in my house when I lived in Cambridge, Ohio, which is kind of crazy. And so the United States was actually preparing to fight a nuclear war and was countenancing the use of these weapons on the civilian population. And so Bert the Turtle was saying, all you have to do is duck and cover. And there's a crazy video about this, which I'll let you look up. It's just kind of nuts. And so I grew up in kind of the era when people were talking about this. But I knew, as someone who, you know, when I got to college, I knew that the explosive power of these weapons and ducking and covering was not going to particularly solve the problems they were looking at. So I really thought that I would never live to to get out of my 20s. I was certain about that because we were talking about using these weapons, and use of them, I think, is just absolutely insane. How did I find hope? How did I find hope in that time? The way I found hope in that time is that people at the time realized this was crazy, and I realized that, and I was not a particularly knowledgeable or well-connected fellow, and so if I was able to realize it, other people were too. And I think we as a society made this decision that when you're standing at the edge of a cliff, you are wise to define progress as one step backwards. So rather than just building bigger and scarier nuclear weapons, maybe we should think about how to get rid of some of the weapons that we have and make sure that we don't use them. And in recent times, there's been a fair amount of effort to do that. The high water point was a treaty ratified by the Senate of the United States in December 2010 that reduced the warheads by 30%, the launchers by 50%. And this was signed by the President of the United States and the President of Russia. This is a fantastic, fantastic thing. But at present, other people are making other decisions. And I'm going to plead with you to please pay attention. The treaties that were passed made us safer. They kept us from having to wake up every morning countenancing Armageddon. And things are changing, and things are changing right now. And you have a lot to worry about. There's pandemics, for instance, to worry about. But I want you, at some level, to pay some attention to what is happening with nuclear weapons and nuclear war. And just be thinking about that, because this is something which we've dealt with before, and this is not the time to shy away from thinking about it. There's a lot to worry about, and I want you just to allocate a small fraction of your consciousness to be thinking about this. Now, next week, we're going to talk about nuclear medicine, and also we're going to have our second exam, and I'm still thinking about what that second exam is going to look like. I will post something this week and share more information. How do we do an exam in the time of social distancing? We'll come up with a good plan that I think that you will appreciate. But thank you for giving me a chance to share some stories with you folks. I wish you all manner of joys, large and small, in this crazy, crazy time. And no, it's been crazy before, and we've gotten through it. That's another thing that gives me hope. We've been through craziness. We've made it through. We've come together as communities. We've come together as a nation. We'll get through this, and we'll have stories to tell. Take care, folks.